Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So, as any of you that subscribe to my channel will know, this episode of course has been delayed quite a lot, been various things going on, but finally I actually managed to get something out, so I'm really kind of pleased about that. It's not entirely the video I was hoping to do, but we're going to start looking at eigenvectors and eigenvalues, and it's going to be spread over a number of episodes. That's just the time that I've had available really to make this episode. I couldn't really bring everything into it, so we're going to split over multiple episodes, hopefully one a week, but I can't promise. We'll just have to see how things go. Anyway, I don't want to make a long introduction, so the one announcement that I do want to make is that, as promised, the code for the linear algebra library as it is so far is now available on GitHub, so I'll put a link in the description below and you can go and check that out easily if you want to look at the actual code that we're going to be talking about, and indeed that we have been talking about over the previous 11 episodes of this series. So that's pretty good, I think. Anyway, today we're going to talk about eigenvectors and eigenvalues, as I've been promising for a while, and just really going to have a quick look at first of all, really what they are, what eigenvalues and eigenvectors are, and then we're going to look at what is I think the simplest and most intuitive method for calculating the eigenvectors of a given matrix, or the dominant eigenvector, I should say, for a given matrix. And then in subsequent episodes, we're going to build on that to look at how we can go on to calculate the eigenvectors and eigenvalues in the more general case. Anyway, hopefully that will be of interest. As always, if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. I do try to make a video roughly once a week, although sometimes that does tend to slip, as has been very much the case recently, but if you subscribe, you don't need to worry about missing anything. Thank you very much. Anyway, without much further ado, let's jump to it and let's have a look at eigenvectors and eigenvalues. Okay, so let's have a look at eigenvectors and eigenvalues. Okay, so the first thing I wanted to talk about really is what are eigenvectors and eigenvalues. And for a given matrix X, the eigenvectors and eigenvalues come from the following equation, where if X times some vector V is equal to a scalar quantity lambda multiplied by the vector V, where lambda is a scalar and is the eigenvalue of the corresponding eigenvector V. But what does this actually mean? To understand what is going on, it is helpful to consider the matrix X to represent a linear transform. Okay, any square matrix can be considered to be a linear transform that can be applied to any vector of the same number of dimensions. For example, in 3 dimensions, we might have the matrix X represented by x11 through to x33, as shown here, and the vector V, V1, V2, and V3, as you see here, and the result, if we multiply X by V, we get a new vector where each of the 3 elements is modified, as you can see here. So the first element is x11 v1 plus x12 v2 plus x13 v3, and so on for the second and the third elements. So here we can say that the matrix X has operated on the vector V to give a new transformed vector, which we could call V hat or whatever. Okay, so if we look back at the equation that we started with, x times the vector v equals lambda times the vector v, we can see that this is telling us that for any matrix X, there is some vector v that, when transformed by X, is equal to itself multiplied by some scalar quantity, lambda. Now, we already know that multiplying a vector by a scalar simply changes the length of the vector. It doesn't change the direction. Therefore, this is telling us that for any matrix X, there exists at least one vector V that is unchanged by the matrix except for its length. In other words, X only acts to scale V and doesn't change its direction. Now, this is not going to be the case for a general vector. It will only be the case with a very specific vector. There'll be at least one. Now, usually you have as many of these vectors as there are rows in the matrix. Okay, so these vectors are actually known as the eigenvectors of the matrix X. And to understand a little bit more clearly what this is really saying, and I actually think this is really incredibly interesting, because what we're really saying is that there exists a set of vectors for any matrix that do not change direction when you multiply them by that matrix, which I think is pretty cool. If we have a look at this 3D illustration that you can see here, this kind of shows an example of what's going on. So here we have the eigenvectors. I've highlighted them in orange. And we have three other vectors that I've defined pointing in different directions for the matrix that you can see here on the screen, 3 by 3, because we're working in 3 dimensions. And if we apply the matrix X to all of these vectors, we see that the orange vectors are simply scaled, or nothing else is changing there, except actually they don't change length because I've normalized them simply so that they stay nice and neat in the animation. But we see the other three vectors in the red, green and blue all change direction. Okay, so we can see the difference. So the vectors that are the eigenvectors are unchanged in terms of their direction when multiplied by x, and general vectors are changed in their direction and in their length when multiplied by x. So that is what an eigenvector is. An eigenvector is simply one of the vectors that satisfies the equation that we began with, x times the vector v equals lambda times the vector v, which means that it is a vector that is only changed in terms of its length when we multiply it by the matrix x. Okay, so how do we actually go about computing eigenvectors and eigenvalues? Well, we can rearrange the eigenvector equation as follows. So we get this x minus lambda I, where I is the identity matrix, multiplied by our vector v is equal to 0. Okay. Now this has a solution if and only if the determinant of x minus lambda I is 0. Therefore, the eigenvalues of x must be the values of lambda that satisfy this equation here, where the determinant of x minus lambda I is equal to 0. And this gives us a route to how we can approach calculating the values of lambda, or the eigenvalues, for any particular matrix of x. Now I should say, I talked about what the eigenvectors were. I didn't actually specifically mention eigenvalues. The eigenvalues simply relate to the extent to which the length of the vector will be changed when it's multiplied by the matrix x. Okay, so each eigenvector has a corresponding eigenvalue, and the eigenvalue simply gives a measure of how much the scale or length of the eigenvector will be changed when we multiply it by x. Okay, so let's consider a simple example. I always think examples make things much more clear. So let's start with a simple 2 by 2 matrix as shown here. X is equal to 1, 2, 3, 4. Okay, and we are going to start with x minus lambda I is equal to 0. And if we put our value of x into that, we get 1 minus lambda, 2, 3, 4 minus lambda, as you see here, is equal to 0. So the determinant of that we know must be equal to 0. Now the determinant of that matrix we can calculate easily enough by hand. If you want to know a bit more about doing that, you can look back at my episode on calculating matrix determinants. But if we do that algebraically, we end up with an equation of 1 minus lambda multiplied by 4 minus lambda minus 6 is equal to 0. And with a very simple bit of rearranging, a bit of algebra, we can rearrange that to lambda squared minus 5 lambda minus 2 equals 0. And we can easily recognize that that is a standard quadratic equation. And therefore we can actually approach solving that really easily, simply using lambda is equal to minus b plus or minus the square root of b squared minus 4ac over 2a, where in this case a is going to be 1, b is minus 5, and c is minus 2. So if we solve that, in this case we get values of lambda for lambda 1 is 5 plus the square root of 33 divided by 2, and lambda 2 is 5 minus the square root of 33 divided by 2. Or, to put them in decimal form, lambda 1 is 5.37 and lambda 2 equals minus 0.37. So these two values, lambda 1 and lambda 2, these are the eigenvalues for the matrix X that we started with, the 2 by 2 matrix of the elements 1, 2, 3 and 4. It has these two eigenvalues, and as I said, these two values relate to how the eigenvectors will be scaled by the matrix X if we multiply them by X. Okay, so we've got the eigenvalues. How do we actually compute the eigenvectors to go with those eigenvalues? Okay, so we already have that x minus lambda I times the vector v is equal to 0, and we can write that out for our sample case here as the matrix x 1, 2, 3, 4 minus lambda times the identity matrix, which will give us this quantity here, times v1, v2 equals 0. If we calculate this sum here, we of course get this, multiplied by v1 by v2 is equal to 0, and then simply we can work that through, and we end up with something like this: 1 minus lambda times v1 plus 2v2 is equal to 0, and 3 times v1 plus 4 minus lambda times v2 is equal to 0, which we can see immediately is a system of linear equations. So we have two unknowns, v1 and v2, and two equations. Therefore, this should be solvable. If we substitute in our value for lambda 1 equal to 5.37, what we get is minus 4.37 v1 plus 2v2 is equal to 0, 3v1 minus 1.37 v2 is equal to 0. Now clearly this is going to have an infinite number of solutions, but we can actually still solve it. We can rearrange the first equation to give that v2 is equal to 2.185 v1, and we can identify one possible solution simply by letting v2 equal 1. In which case v1 is going to be 1 over 2.185, which is equal to 0.458. And therefore we have that for lambda 1, the eigenvector can be given by 0.458 and 1. Now this really illustrates a key point. There are actually an infinite set of eigenvectors that will all point in the same direction, but will have different scaling. So we could have chosen any value here for v2, and it would have simply scaled our value of v1 proportionally. So obviously, the scaling doesn't really matter. It doesn't affect the direction of the eigenvector. It's the direction that's really important, which is why this way of solving it is appropriate in this case. Okay, so we then repeat the process for lambda 2 equals minus 0.37, which gives v2 equals minus 1.46 and 1. It's just using the same method. So we know that for the matrix x equals 1, 2, 3, 4, we have that lambda 1 equals 5.37 and lambda 2 equals minus 0.37. And the two eigenvectors are v1 is equal to 0.4581 and v2 equals minus 1.461. Okay, so that was pretty straightforward for a 2 by 2 matrix. What about a larger matrix? Well, for 3 by 3, we could still find the roots of the polynomial for the values of lambda, in most cases. But for polynomials of degree greater than 3, there is actually no general solution. Now, we could approach this by simply finding the roots of that polynomial numerically. So we could, for any matrix, we could derive that polynomial known as a characteristic polynomial. And we could then numerically calculate the roots, which would give us the values of lambda, and then we could compute the eigenvectors as we've just seen. However, numerically finding the roots of polynomials is not without its own problems, and in fact, that would easily be another episode just on its own. However, luckily there are some other ways that we can go about computing the eigenvectors. So I want to start by looking at what I consider to be the very simplest and most intuitive of these methods, which is the power iteration method. Okay, so the power iteration method will always compute the dominant eigenvector, that is, the eigenvector which has the largest magnitude eigenvalue. On its own, it will only find this one eigenvector. However, that actually can still be very useful. It is the simplest and probably most intuitive method, so I think it really makes quite a good starting point. Okay. So the power iteration method is, as its name suggests, an iterative method where we're going to iterate this equation. It's actually really very simple. So we know that we're going to start with a given vector v. Okay, so start with a vector v0. We apply the matrix x to it as a linear transform, so simply multiply them. That's this x times a vector vk. Okay, and then simply divide by the magnitude of the result to give vk plus 1. So vk plus 1 is equal to x times vk over the magnitude of x times vk. And that's it. If we simply iterate that repeatedly, we will end up with a progressively good approximation of the dominant eigenvector. So actually you can see quite intuitively what's going on here. We can start with any vector, we multiply it by x and then normalize it, and simply repeat that process over and over again, and that vector will converge to the dominant eigenvector of the matrix X, which I think is actually pretty cool. So let's have a look at trying to solve that with our 2 by 2 example that we looked at before. Okay, so starting as we did before with x equals 1, 2, 3, 4. Okay, now we can start with v0 equal to anything we want. It's common actually to use a random vector, but in this example I'm going to start with v0 equals 1, 1. Okay, so for v1, the first iteration, we have our matrix x, 1, 2, 3, 4, multiplied by our vector v0, which is 1, 1, divided by the norm of the matrix x multiplied by the vector v, which gives the vector 3, 7 divided by the square root of 3 squared plus 7 squared, which gives v1 equals 0.3939, 0.9191. Okay, then we simply repeat that process again for V2, as you can see here. Now V2 is 0.4173, 0.9087, and we repeat it again for V3, and now we have 0.4159, 0.9094. So if we look at that sequence, these are the values that we get, starting with V0 at 1, 1, going through to V3 for 0.4159 and 0.9094. Which we can see is converging to the same result that we had before, allowing for rounding errors. Obviously, I've worked these out by hand, so there's some significant rounding errors going on. But if we allow for that, we can see that this process is gradually converging. Okay, so to compute the eigenvalue to go with that eigenvector, if we start with our equation, again, x minus lambda I times the vector v is equal to 0, which for this example, we see gives us this. 1 minus lambda 2, 3, 4 minus lambda multiplied by that. Now, considering only the first equation, as we saw before, we can rearrange that to give 1 minus lambda times 0.4159 plus 2 times 0.9094 is equal to 0, which of course we can then rearrange to give a value of lambda, which is 5.3732, which is, of course, the right answer. What about, how does this process look if we were to look at a bigger example? So let's have a look at an animation of how this process works for the 3x3 matrix that we looked at previously. So we can see this animation here if we just zoom out slightly so that we can see what's going on. Now we can see as we work through the iterations, you can see the iteration number there in the top right, you can see how the three vectors are generally converging towards the dominant eigenvector. So as before, the three eigenvectors are shown in orange and the other vectors are in red, green and blue. And we can see that as we iterate over the system, the three separate red, green and blue vectors all converge to the same dominant eigenvector of the matrix X, which I think serves as quite a good illustration really of how this process works. Note that they do flip around, and there is actually the case that they do change sign as well sometimes, but the direction of the sign of a vector is really simply a scaling by -1, so it doesn't actually change the validity of the result. And in order to create this animation, I have compensated for that so that they do point in the same direction. Otherwise, it was kind of headache-inducingly flashing, which was not good. Anyway, but yeah, so they do flick around, but they do all converge to the same eigenvector, which is the key point. Okay. So anyway, and just to go back to this very briefly, in the general case, we can compute lambda by considering the first of the set of equations that we get from x minus lambda I times the vector v equals 0, which we can see, if you work this through with a pen and paper, you can follow it through. You end up with the first element of x, x11 minus lambda times the first element of v, v1, plus x12, v2, plus so on up to x1n, vn equals 0. And you can then rearrange that to give x11 minus lambda is equal to this, and finally rearrange to give lambda is equal to this. So we have a cumulative sum term here that would be easy to calculate in code, and then we simply divide that by v1 and add x11. Which is pretty straightforward to do. Okay, so that's really all of the basic introduction that I wanted to give for eigenvalues and eigenvectors, which I really hope was useful. Let's have a look at how we can actually go about implementing the power iteration method in code. Okay, so this is the code that I've created. It's, as all of the code in the QB linear algebra library, this is a header file, and I've written the code in the header file because we're using templates. I've talked about that before. One thing to note, actually different from the previous episode, notice now that qbmatrix.h and qbvector.h come from the same place. That's because this is now in one library, which, as I said at the beginning, you can now download from GitHub if you wish. So link in the description below if you want to go and look at that. So this code is all up there. So as before, we define an error code. We have just one at the moment, which is for matrix not square, simply equal to -1. And then we come into the qb_ig underscore pit for power iteration function that I've created, accepts as input a const to a QB matrix 2 object, which we're calling x, and we have two outputs being the eigenvalue and the corresponding eigenvector. So eigenvalue is just a numerical value of type t, and eigenvector is a QB vector object also of type t. So the first thing that we do is make a copy of the input matrix, because there are still some issues with the const in the matrix class. This code does need a fair degree of refactoring, but I will work on that. And like I say, the code up on GitHub is presented very much as a work in progress. So first of all, we verify that the input matrix is square. If it's not square, then we simply return our error code. We use the isSquare method from the matrix class to do that. We then set up a random number generator. We've looked at these before. We're going to use this to create the random starting vector for our solution. And so then we calculate the number of rows. This says the number of eigenvectors and eigenvalues that we compute will be equal to the number of rows in the input matrix. Now that's true, but of course we're using the power iteration method, which is only going to give us one eigenvector and eigenvalue, so that doesn't really matter. But we extract the number of rows from the input matrix. We then create an identity matrix of the same dimensions, okay, just like that. So we set up a QB matrix 2 object of type T called identity matrix of n rows by n rows, and we use the setIdentity function within the matrix class to create the identity matrix. And now we're actually going to compute the eigenvector, and as you can see, this is incredibly short. This is a very, very easy to implement algorithm, which is why I think it made really quite a nice starting point actually for this. So the first thing we do is create our initial vector v. So we set up a QB vector of type T object called v with num rows, and then we simply loop through every row and we set it to some random value extracted from the random number generator, exactly as we've seen before, static caster type T. Okay. And we're simply going to then loop over the required number of iterations. Now, I've done this for a fixed number of iterations of 1,000. It's not strictly the proper way to do it. Really, you should put in some kind of test, a test for convergence. So you could simply look if it's settling to a value, or otherwise compute an error in some way. But for what I want to do, this is plenty good enough. So I set num iterations equal to 1,000, which is quite a lot, but it makes sure we're going to get the right result. So we first of all set up our QB vector object of v1, okay, which is going to be a copy of v that we're going to use, and then we're going to loop over the number of iterations, and each time through that loop we simply set v1 equal to input matrix multiplied by v, okay. So because we took care of all of the complicated stuff with matrix multiplication in the matrix class, go back and have a look at that episode if you haven't seen that already. This is very easy to do. We then normalize v1, and then we simply set v equal to v1, and then we just go through that loop again, and really that's it. And after the required number of iterations, we have our eigenvector, so we simply have eigenvector equals v1, that is the output, and there we go. And then we simply use the formula that I just showed you to compute the corresponding eigenvalue to go with that eigenvector. So we set up a cumulative sum variable of type T, initially static caster 0, and then we loop over the number of rows and calculate the cumulative sum, which is simply equal to input matrix get element from the first row, the ith column, times v1.getElement I, noting that I starts from 1, not from 0, okay? And then the eigenvalue is simply the cumulative sum divided by the first element of v plus the first element, or 0th element of the input matrix. And that's it. That's really all it is. It's very simple and very short. Okay, let's have a look at the code that I've also created to test this, which is also included in the repository. Okay, so this is the test code that I created, which is also on the GitHub repository. If you go and have a look at that, you can find it there. It's pretty standard for how I do all of my test code, really. It includes QB matrix, QB vector, and QBi.h, all from the parent directory or folder. For where this is. If you look on the repository, you'll see how the code is organized. And then we just have functions for printing a matrix and printing a vector, stuff I've talked about before in previous episodes, and not much to talk about there. And then so in the main, this is simply we're going to do our test. Actually, although it says with a simple 3x3, we initially do the test with a 2x2 matrix 1, 2, 3, 4 that we've been working with in the examples that we've just seen. So we simply define a std vector object with our data, and then we use that to create a QB matrix 2 object of type double into which we pass that data. Okay, so that gives us a 2x2 matrix, and we print that out, and then we compute the eigenvectors and eigenvalues. So we simply have a double variable here for eigenvalue, and a QB vector of type double variable eigenvector for the eigenvector. And then we just call our QB eig_pit for power iteration. We pass test matrix, eigenvalue, and eigenvector, and that's it. And then we simply print vector to display the result, and of course C out there to display the eigenvalue. And that's all of the code that we need. So let's have a look at what happens if we run that for the very simple case that we have there. Okay. Okay, so I'm at my terminal window, so we can just have a quick look actually at how the code is organized. So this is the main folder. If you clone this from GitHub, this is what you're going to see. So we have the functions qbig.h, qblinssolve.h, qblsq.h, qbmatrix.h, and qbvector.h, as we would expect, as we've been talking about in the previous episodes. And we have a directory or a folder here called test code. So if we go into that, have a look at that. Okay, there we see this has all of the various test functions that we've been talking about in previous episodes. Of course, the one we're interested in today is this one test code underscore qbig.cpp. So we're going to go ahead and compile that. So do g++ minus o test code underscore qbig and test code underscore qbig.cpp minus std equals c++17. Okay, let's compile that. Okay, now if we run it, we should see the result for the simple 2x2. Oops, code qbig, like so, and indeed we do. We get the eigenvector 0.416, 0.909, that's as we worked out before by hand, and the eigenvalue of 5.372. Okay, so let's just go back to our code quickly. Right, and we can have a look at just how this works if we put a simple 3x3 matrix into it, such as this one. Okay, so simple 1, 2, 3, 4, 5, 6, 7, 8, 9, a very simple 3x3, just to demonstrate that it does indeed work in that case. We go back to our terminal window, let's rerun our compiler, and rerun our code, and there we go. So in that case we get the eigenvector there, 232, 0.232, 0.525, 0.819, with an eigenvalue of 16.117. Now I know, because I've looked at this in other software, that that is indeed the right result. Okay, so that really very simple algorithm. It only returns a single eigenvector and eigenvalue for a given matrix, but it does return the dominant or the most significant eigenvector, and that in itself actually can be very useful. But I think is enough to talk about, at least for this first episode, looking at eigenvalues and eigenvectors. Okay, so that's really everything I wanted to talk about today. It was, as I say, a shorter episode than I was really planning originally, but I think we've covered at least the basics of what eigenvalues and eigenvectors are, and we've looked at one way that we can quite easily estimate or compute the dominant eigenvector for any given matrix, which is quite interesting. So in the next episode, we're going to look at how we can expand upon that to work with the more general case, which hopefully will be of interest. So do keep an eye out for that. I'm not going to promise that it will be available next week. I'm going to try to do that, but there's a lot of other things going on with my day job and so on at the moment, so we'll have to see. I'll do my best. Anyway, I really hope you've enjoyed this video. It's been a great deal of pleasure making it, and I really look forward to seeing you in the next one. Thank you very much for watching. Bye.